Hello again, everybody. Welcome back. This is our last example, 1016, and here we're actually going to be applying some values and actually getting our calculators out. But we're going to be using the same kind of principles that we have in the past few examples. That is simply conservation of energy. But we are going to be accounting for not just linear kinetic energy, not just rotational kinetic energy, but also gravitational potential energy as well. So we've got an initial position and a final position right here, and some values that we can actually put in. Well, once again, if we have an initial and final position, if we're dealing with gravity, and gravity is the only force that is acting on our yo-yo right here, then we can have energy initial, and energy final, and set them equal to each other. All right. I'm not even going to write down our knowns quite just yet. I want to get just right into writing our conservation of energy out, and then later on we can write down our knowns. All right. So energy initial equals energy final. The question is, what kind of initial energy does it have? What kind of final energy does it have? Okay. Well, at the top right there, before the yo-yo is released, it has no velocity right here. Okay. So the kinetic energy, or the linear kinetic energy, I should probably write that on the left-hand side. Kinetic linear equals 0. So if it's not rotating, we can also say that the rotational kinetic energy equals 0. But it does have some energy, and that is gravitational potential energy. And of course, that equals mgh. Okay? Finally, down at the bottom, what kind of energy does it have? Well, the nice thing about dealing with gravitational potential energy is that we can set 0 equal to whatever we want. So we're going to call this level right here 0. So we can say that finally at the bottom, and I'm going to write, I'll just write it down below. We can say that the potential energy due to gravity equals 0 because it's dropped through the whole height that we care about. Okay? So no more gravitational potential energy, but it does have two kinds of kinetic energy. It is dropping straight down, as tends to happen with a yo-yo. You kind of throw it downwards and it drops straight down this string. Okay? So it's got linear kinetic energy is 1/2 mv squared, but it also has rotational kinetic energy, and that is k sub r. Let me try that again. K sub r, rotational kinetic energy equals 1/2 I times angular velocity squared. Okay? Now we're solving for the linear speed. All right, so it's probably true that we'll have to take this angular velocity and convert it into v right here. But for right now, let's just simply write out all of our conservation of energy statements in a straight line, in a linear statement. Okay? So our initial energy is mgh. That comes from this right here. The initial energy of the system is all potential. Equals, all right, linear kinetic energy, right? 1/2 mv squared. 1/2 mv squared plus our rotational kinetic energy, which is 1/2 I times omega squared right there, or our rotational velocity that it has. Okay? Well, we're given a bunch of things. We're given a whole lot of stuff right here. We have the moment of inertia of the yo-yo. We've got the mass of the yo-yo. We've got the radius. Now this is interesting. You'll notice that a yo-yo usually has a groove in it, and so the actual radius around which it spins is this little teeny tiny guy right in there. All right, that's the radius. And we're told that that is 0.0064 meters, or what, 0.6 of a centimeter, 6.4 millimeters. And we know the height that it's dropped through, and we're going to be asked to find the linear speed. So, again, I'm not going to write them down quite just yet. Let's solve for our linear speed, and then we'll just put our values in as we get them, okay? So, this omega right here, this angular velocity, we can take that and turn that into terms of velocity squared, right? Because angular velocity, I'll write this over on the far right, equals v over r. So therefore, angular velocity squared is linear velocity squared over radius squared. Okay? So let's go ahead and do that. So we have mgh equals 1/2 mv squared plus 1/2 times I times v squared over r squared. Okay? Or you could just say IV squared over r squared. Okay. Well, let's get rid of these 1/2s. All right, we've got a 1/2 here and a 1/2 here, so we'd have to multiply by 2 on that side, which means this would become a 2 over here on the far left. So it's going to come out to be 2 mgh equals mv squared plus I times v squared over r squared, like so. All right, now remember we're solving for our v squared, or well, we're solving for our v. So let's go ahead and factor that out. 2 mgh equals v squared comes out, and then in the parentheses we have m times, m plus I over r squared. I'm probably going to start putting little serifs on the I right here because it looks like a 1. I should probably put the little serifs on there. Okay. Well, we have the v squared all by itself. Let's get this whole mess away from it by dividing it down, right? So, and I'm also going to switch the sides too. So I'm going to write v squared first. V squared. So this whole thing gets divided down beneath 2 mgh. So it's going to be 2 mgh over mass of the yo-yo plus the moment of inertia of the yo-yo divided by the radius squared. Okay, we're almost there. And again, we've gotten to this point simply because of conservation of energy. If we account for all the energy initial and all the energy final, set them equal to each other, and then it's just algebra from there on out. All right, we have the mass of the yo-yo, we know what g is, we know what the h is, we know what our I, our moment of inertia is, and we know the radius. Last thing we need to do is simply just take the square root of that whole thing, right? Velocity, the linear velocity, the linear speed of the yo-yo as it has dropped through that height is going to be the square root of 2 mgh over mass plus I over r squared. Fix my plus sign right there. Okay? All right. I think I just about left the right amount of space. I'm going to have to write my final answer up above. But let's put our values in now. We know what our m is, right? So it's going to be 2 times, what's the mass? Mass is 0.056 kilograms. 0.056 times our height that it drops through, that is 0.50 meters. 0.50 meters right there. Divided by this whole kind of messy stuff inside the parentheses. The mass, which is, again, 0.056. 0.056 kilograms. I'm leaving our units out. Plus. Okay, now this is our moment of inertia. And we're told this is 2.9 times 10 to the negative third kilogram meters kilogram meters squared. This looks like a solid disc, but remember, yo-yos have a groove in there. And so that'll be a little more difficult to actually figure it out using the values that we're given or using our table that we keep flipping back to. So thankfully, we are told that the moment of inertia is just that value right there. 2.9. I'm going to put 2.9 e negative 3. You guys should know that that means times 10 to the negative 3. All right. Divided by our radius squared. And our radius is 0.0064 squared. 0.0064 squared. I probably could have written that in a scientific notation too. That would have made a little bit more sense. But that whole thing in there gets square rooted, and that's going to be our final answer. So like I predicted, I'm probably going to have to write our final answer up here. I'm going to punch those numbers. I'm going to ask you to do the same thing, and hopefully we get the same answer. Let's see what we get. All right, so I've keyed that in. That was a pretty messy equation right there, but I think I'm looking at my calculator. I think I got all the parentheses and everything in the right place. By the way, keep in mind your parentheses. You've got this whole numerator. That's not too bad, but the denominator is all one big thing, and you've got a plus sign in there, and you've got this fraction. Keep in mind your parentheses. Here's what I get: 0.028 meters per second. That is our linear velocity. That's what the linear velocity is that I get keying all of this into the calculator. And I'm double checking my work. I think I have it right. Let's ask ourselves, does that make sense? So 0.028 meters per second. So 2/100ths of a meter. Well, that's like 2 centimeters per second. Well, I guess as it gets down towards the bottom, it might actually, well, at least that's reasonable. I'll have to double check and see what the actual final answer is, but that's what I get. And you get the same thing, then it means we must have done the same math. So at least it's not millions of meters per second or anything like that. All right, so it's reasonable. It's not too tremendously fast. It might be the same rate that you might drop a yo-yo. So that's the final answer that I get. Barring any calculation errors, that's the process that we would use to get it done. So that's our last example for this chapter, Chapter 10, Rotational Kinematics. It's just conservation of energy. Thanks for following along once again, and if you have any other questions, please make sure you come and see me, and I'll be glad to help you out. Thanks for following along. I'll see you on the next one, probably in the next chapter. Take care.